All right, let's talk about something every senior database expert has to wrestle with at some point: optimizing that incredibly stubborn, slow-running SQL query in an Oracle environment. Welcome to this explainer. You and I both know that tuning SQL isn't just about throwing indexes at a table and crossing our fingers. We're going to get past the guesswork today. We're going to break down the actual mechanics of the Oracle cost-based optimizer, extract its execution blueprint, and read those terminal diagnostics like the pros we are. Okay, let's dive into this. Here is our methodical progression for the day. First, we've got the optimizer mindset. Then, generating the explain plan. Third, decoding the execution output. Fourth is spotting high-cost operations, and we'll wrap up with professional SQL tuning practices. Let's get right to it. Section 1. The optimizer mindset. Thinking like the CBO. Look, before we even touch the keyboard to tune a query, we have to understand the why. We literally need to see the code exactly the way the Oracle optimizer sees it. At the very core of this whole thing is the cost-based optimizer, or the CBO. Basically, its entire job is to calculate an estimated value that we call cost. And this cost is strictly proportional to the expected resource use. It looks at the available access paths, analyzes the data dictionary statistics for your tables and indexes, crunches the numbers on estimated I/O, CPU, and memory overhead, and then it simply picks the plan with the lowest cost. It's really just one giant mathematical balancing act. But here is the kicker. The absolute most critical piece of information the optimizer produces is the cardinality estimate. This is just the number of rows the optimizer expects a specific operation to return. So why is this so crucial? Well, because a bad estimate here creates a massive domino effect. Every single downstream decision, from the join method it picks to the memory it allocates, relies entirely on this number. If your cardinality is off right at the start, your query is absolutely headed for a massive performance bottleneck. Section 2. Generating the explain plan, extracting the blueprint. Now that we know how the CBO thinks, we need to know how to actually extract its roadmap. The SQL execution lifecycle really boils down to 3 sequential steps. First up, the optimizer generates a bunch of potential execution plans using the available paths and any hints you might have thrown in. Next, it estimates the cost for every single one of those theoretical plans based on your dictionary stats. Finally, step 3, it picks the lowest cost option. Our entire job as tuners is to intercept and analyze that winning plan. To grab that plan, we've basically got 2 primary methods. The explain plan command is our standard go-to. It shows you the theoretical plan without actually executing the query. But $SQL plan is honestly the preferred route for deep diagnostics. It looks right into the cursor cache to show you the genuine actual execution plan that the database just used. Because let's face it, when performance is on the line, we need to know what actually happened, not just what the database thought might happen. Section 3. Decoding the execution output. Terminal window diagnostics. Now, what's really interesting about this slide is getting into the actual mechanics of reading these outputs. If you're looking at standard DBMS_Xplan output, it's going to look a lot like this monospace table. The golden rule for reading an execution tree: always start from the most indented operation and work your way outward and upward. So in this example, operations 2 and 3, those full table accesses for T2 and T1, those happen first. Then their results feed up into the hash join at operation 1. As you read through this, you want to keep your eyes glued to the rows and cost columns. If you suddenly see an unexpected, massive explosion in the rows column, you've just found your first major clue that something is terribly wrong. To catch those runaway costs, we have to leverage the format parameter in the DBMS Xplan package. Tweaking this unlocks some incredibly deep diagnostics. For example, if you pass all stats last, it literally displays the actual rows returned right next to the estimated rows. That is absolutely invaluable for spotting those cardinality misestimates we were just talking about. Another one you've got to use is plus alias, which pulls up the query block names. Let's talk about those query block names for a second. Oracle automatically names every basic unit of your SQL, like an inline view or a subquery. So your outer query gets tagged as SEL$1, a subquery gets SEL$2, and so on. When you are staring down a monstrous 100-line execution plan, utilizing that plus alias format is a total game changer. It lets you instantly isolate exactly which subquery is responsible for a massive chunk of your cost. Section 4. Spotting high-cost operations, culprits, and cures. We know how to read the blueprint. Now let's find the physical operations driving up our I/O and CPU. The most common culprits we deal with are join strategies, right? Specifically, nested loops versus hash joins. Nested loops are totally fine, even fantastic for small result sets, say around 1,000 rows, because they efficiently use index scans to find matching rows. But if you try scaling that up to 1,000,000 rows, that nested loop turns into a nightmare of 1,000,000 individual index lookups. When you hit that scale, forcing a hash join is usually the way to go. The database just builds a hash table on the smaller dataset, probes it against the larger one, and your I/O drops significantly. But hey, it isn't just about your joins, it is heavily about how your data physically sits on the disk. Jonathan Lewis points this out perfectly in his text on cost-based Oracle fundamentals. You have to consider the clustering factor. It's totally counterintuitive, but how randomly scattered your data is across disk blocks often impacts the optimizer's calculations way more than the actual index structure does. If the CBO thinks your data is tightly clustered, your index cost stays low. But if the data is scattered everywhere, that cost skyrockets, and the optimizer might just completely ignore your beautiful custom-built index and opt for a full table scan anyway. Section 5. Professional SQL Tuning Practices. Standard Operating Procedure. So the crucial point is, how do we translate all these diagnostics into a safe, reliable methodology? Well, we have to start by asking ourselves a very serious question. Does the explain plan really show the exact execution plan that will actually be used in production? Actually, Oracle expert Maria Colgan hits the nail on the head here. She says, under certain conditions, the plan shown by the explain plan command can be different from the plan that will actually be used when the query is executed. And we know why, right? Differences in bind variables, underlying schemas, localized cache hits. Trusting a purely theoretical plan is incredibly risky. You absolutely have to verify those changes. And this brilliantly illustrates why we lean on the autotrace utility. When you need to validate a tuning hypothesis, autotrace gives you the deep statistics you need. You can use set autotrace trace-only explain to just see the execution path without dumping thousands of rows into your terminal window. Or use set autotrace on statistics for those deeper execution metrics. But above all else, always test heavily in a stable, non-production environment before deploying to live systems. We've covered a ton of ground here, from getting into the optimizer's mindset to pulling apart DBMS XPlan outputs line by line. I want to leave you with one final thought to chew on. Are your queries actually taking the optimal path, or are they just taking the first one they found? Never blindly trust the defaults. Get in there, actively inspect your Oracle environments, pull those execution plans, and take full control of your SQL performance.